Okay, let's go into the big example of this section, which is decision making with an experimentation. In this scenario, we're going to think about more realistic information that we might gain, where we gain additional information, but not perfect information about those states of nature. So um, in this case, we're going to kind of think of the management at Silicon Dynamics, the company might hire someone to do market research for them. Okay, and so in this case, we're going to say that market research costs $1 million. Um, and it can have two sort of outcomes from that market research. Either the market research can come back and say favorable market conditions, or they can come back and say unfavorable market conditions, where sort of favorable market conditions would be more predictive of selling 100,000 computers, whereas unfavorable market conditions would be somewhat predictive of selling only 10,000. Okay, but these two kind of findings, we'll call them experimental findings, are not 100% accurate, right? They don't perfectly tell us what the state of nature will be. Okay, if they were, then it'd be like the last example where we had perfect information. But from past experience, we know that when the market research says, or when the true state is a poor market rollout, then the market research tends to be correct 85% of the time. And so if the actual state is only selling 10,000, the probability of saying unfavorable market conditions is 85%. So these are what are called conditional probabilities. And the way you think about these conditional probabilities that are kind of written with this vertical bar here, these are kind of probability of a finding, one of our experimental findings, vertical bar, one of our states. This is the probability of the experimental outcome. And then this vertical bar means given or knowing the state. Okay, so we assume it's in the state. If we assume or know that it's in the state, then the probability of that finding is, in this case, 0.85. Okay, the thing to note is that if you kind of fix the given, so these are both given the same state, these two probabilities will add up to 100%. Okay, so there's two possibilities knowing the state is equal to 10,000 computers sold. Either it's going to be a finding of unfavorable market or favorable market. And if the state is 10,000, there's an 85% chance of unfavorable market and a 15% chance of a favorable market. Okay. On the other hand, when the true state is a good market rollout, then it's only accurate 65% of the time. And so in some case, it's easier to read the warning signs that things are not going to go well than they are to sort of read the warning or read the positive tea leaves and know when something is going to go well. Okay, so it's harder to predict a good market rollout. Okay, so these are what are called conditional probabilities, in that they're conditional on the state of the system. You can also think of these as accuracies. Okay. If we think of selling 100,000 as sort of our positive state of what we're trying to predict, you might consider this probability here as what's called our true positive rate, where the actual state is positive and we predict positive. Okay. This one up here we might think of as our true negative rate. Let me think. Okay, so this one we're predicting a negative outcome, but it's actually a positive outcome. This would be what we call a false negative rate, and this one would be a false positive, where we're predicting a positive outcome, a favorable outcome, but really it's not. And so this would be our false positive rate. Okay, and so we can think of these as our accuracies. It's not always true that the accuracies for the actual negative class are equal to the accuracies in the actual positive class. Sometimes they are, sometimes they're not. Okay. So those are the conditional probabilities. Then what we need to do is use those conditional probabilities to get to what are called posterior probabilities. So posterior probabilities essentially flip the order of state and finding. So given a finding, so once we hear the finding, we want to know what's the probability of selling 10,000 or 100,000 computers, right? If they come back and say favorable market conditions, what does that mean about the probability of selling 100 versus 10,000 computers? Or if they come back and say unfavorable market conditions, what does that mean about the probability of selling 100,000 or 10,000 computers? Okay. So here's the formula, and this is called Bayes' theorem, and allows us to essentially switch the order of what we know versus what we're computing a probability of. Okay. And you'll notice here, we're talking about probabilities of a given state, knowing a finding. So after we've heard the finding, and it's computed on this side where we have all our states given, right? So these are each of our conditional probabilities. So this here is a conditional probability from up here. This probability of state I, that's a prior. Okay. And then we're going to divide by the sum of all these same things as these terms summed over all the different states. Okay. Now, it helps to do this in a couple steps. And so we're going to do this in a couple steps. The first step is to compute what are called the joint probabilities. So step one is to compute the joint probabilities. The joint probabilities are what are on the top of this fraction here. Okay. And this probabilities are the probability essentially of that state and that finding. Okay. And so let's maybe jump into an example. So probability of finding equals UMC and state equals 10K. So note that this is different than finding given state equals 10K. Okay. This is going to be the probability of finding equals UMC given state equals 10K times the prior probability of state equals 10K. Can I fit it in there before I run off the edge of the paper? Ooh, barely. Okay. So that's essentially one of the terms that looks like the top of the fraction. Okay. And in this case, that's going to be this conditional probability is this number 85% up here. And then the prior probability of only selling 10,000 computers is 0.6. So multiplying those, we'll get 0.51. Okay, so there's a 51% chance of receiving a finding of UMC and the state being 10K. Okay, and now we need to essentially repeat this for all the other combinations of finding and state. So we can look at probability of finding equals, I'll kind of keep moving through this table. So we'll do FMC and state equals 100K. Oh no, 10K. Ugh. Here, I'll write that underneath 10K. I'll take this false positive rate of 0.15, multiplied it by the probability of being in the 10K state. And so that's going to be 0.6, and that's going to give me a value of 0.09. Okay. Now, these are both the possibilities with state equals 10K. And what you'll notice about these two numbers is they add up to the prior probability of being of 0.6. Okay. Now let's do probability of finding equals, let's do this one. So FMC and state equals 100K. So I'm going to take this rate here of 0.65, multiply it by the prior probability of 100K, which is 0.4. And that should give me a value of 0.26. Okay. And then my last joint probability is finding equals UMC, unfavorable market conditions, and state equals 100K. And that's going to be the 0.35 times the 0.4. Okay, the 0.35 came from here. UMC given state equals 100K multiplied by the prior probability of state equals 100K, which is 0.4, and that gives us 0.14. Okay, and I've kind of got these calculations off to the side. I'm not just rattling these off the top of my head. Have a calculator on the side as you're doing these computations, but I will point out some quick checks you can do along the way that are just good things to do, is that the sum of these two that have the same state should add up to the prior probability of that state, which is 0.4. The sum of these two, which both have the state equals 10K, add up to 0.6. Okay, so these are our what we call joint probabilities. The next thing we want to do is compute what's called the unconditional probabilities. I like to think of these as our probabilities of our findings. Okay, and so we're going to look at, and these are going to be the bottoms of the fractions. And so you'll notice the bottom of the fraction sums over all states that have that finding. Okay, so these ones we'll write as probability of a finding. So probability finding equals UMC is going to take the probability that it's UMC and state equals 10K plus the probability that it's UMC and state equals 100K and add those two probabilities together. Okay, so this is going to be, here, I'll write it out. Probability, I'll write this out. UMC and 10K plus probability of UMC and 100K. And so that's going to be 0.51 plus 0.14. Okay, taking these two probabilities that both have the finding equals UMC. And that should give us 0.65. Okay, bend my paper a little bit. And let's do that for the other possible finding. So we're going to want probability finding equals of favorable market conditions. And we'll add together the two joint probabilities that both have favorable market conditions, and that's going to be the 0.09 plus the 0.26, and that gives us 0.35. Okay, I will say it's a complete coincidence that this 0.65, 0.35 matches up with the fact that we had 0.65, 0.35 up there. Pure coincidence, pure coincidence. Doesn't usually happen. But these unconditional probabilities tell us what's the likelihood of getting that finding. Okay, from our accuracies and our prior probabilities, we know that it's actually more likely to get an unfavorable market condition finding than it is to get a favorable market condition finding. Okay. So kind of given our accuracies and our prior probabilities, we can actually compute the likelihood of each of the experimental findings. Okay. Our next thing that we're going to need, and I'm going to have to move on to a new sheet of paper. I didn't leave myself quite enough room. Is then our posterior probabilities. And so looking at the formula here for posterior probabilities, here, maybe let's expand this formula a little bit. So this is going to be joint probability over unconditional. Okay, where we just need to choose the correct joint over the correct unconditional for the given state and finding that we're trying to do a posterior probability for. Okay, let's get this centered up. Okay, posterior probabilities. And these are what we're aiming for. So the posterior probabilities are probabilities of a state. So state, let's do state equals 10K, given we know the experimental finding. And these become useful once we sort of get those experimental findings. So let's do given finding equals UMC. Okay, we're going to take the joint probability that is the and of these two things. So this is the probability of UMC and 10K. I'm going to kind of suppress the state equals and finding equals, divided by the probability of just the finding. So the probability of UMC. So this is going to be, that's a joint probability there. And this is that's an unconditional, or the probability of just a finding. Okay, and so in this case, that's going to be UMC and 10K. That's going to be this joint probability, which we computed to be 0.51, divided by the probability of UMC, and that's this one, which is 0.65. And then that should give us, I gotta kind of look at my notes here, I'll say about 0.785. Okay, so about 78.5% chance of getting, selling 10,000 computers if the market research comes back with a finding of unfavorable market conditions. Okay. Let's go ahead and do the rest of the posteriors. So let's do probability state equals, let's keep the finding equals UMC for now. So let's do state equals 100K given finding equals UMC. That's going to be, we're going to take the joint probability of 100K and UMC. So looking here, UMC and 100K, that's the 0.14, divided by the probability of just the finding UMC. That happens to be the same 0.65 that we used up here. And so that ratio then gives us 0.215, or approximately 0.215. Okay, the thing to note here is because these two have the same denominators and they're top of the fractions add up to the 0.65 as well. These two probabilities should add up to 1. Okay, and that's also because they're both given the same finding. These are the probabilities of the two outcomes, or the two states of nature. Okay, let's do it for the other finding. So probability state equals 10K given finding is favorable market condition. So I need to find the joint probability that has those two things. So let's see, state equals 10K and favorable market condition. That's a probability of 0.09. And we're going to divide it by the probability of just the finding. And so favorable market condition finding is 0.35. And then this gives us an approximate probability of 0.257. Okay, let's do that for we got one more posterior. This one would be state equals 100K. Given our finding is favorable. And this would be the, state 100K favorable market condition, that gives us this 0.26 over finding the probability of a favorable market condition finding. That's still the 0.35 there. And that's going to give us approximately 0.743. Okay, and these two add up to 100% because they're both given the same information. Okay, so whenever you have two probabilities that are given the same information and they're the only two out states, then they should add up to 100%. Okay, so let's summarize these posterior probabilities in a table. And then I'll maybe also show you the tree diagram way of computing these. Okay, so let's make a table where we look at our two states of nature. So 10K and 100K. These are our states. And then let's look at our two findings. So these are not our alternatives at this point, but our findings. We can either have unfavorable market condition or favorable market condition. These are our findings. And kind of let's put the values that we computed into this table. So this is 0.785 versus 0.215. And this is 0.257 versus 0.743. And what I'll kind of put down here is just our priors, which were 0.6 and 0.4. And then what I'll kind of draw your attention to is everything in this column is a probability of selling 10,000 computers. Okay, but our prior is using no prior information. The UMC is using that unfavorable market condition forecast and computing the probability of 10,000 computers. And then this is given the information of a favorable market condition. And so relative to the prior, if the probability of selling 10,000 computers under an unfavorable market condition increases, and the probability of selling 10,000 computers under a favorable market condition decreases. And then with 10,000, we see that this probability is less than the prior. And so essentially, if there's an unfavorable market condition, the probability of selling 100,000 computers goes down. But if there's a favorable market condition, it goes up quite a bit. Okay, and so we can kind of see unfavorable market condition information moves our priors more towards selling 10,000 computers. when there's a favorable market condition, it moves from our priors more towards having more probability on selling 100,000 computers. Okay. It doesn't move all the way to 100%, 0%. That's what would happen if we had perfect information. But when we have imperfect information, where we don't have 100% true positive rate and true negative rate, then it's just going to move those probabilities more towards one end or the other. And so we get some value, but we don't get perfect information. Okay. Let's then move on to, I'll show you a trick on how you can compute these with a probability tree. Okay. So the probability tree, you start off with your priors. Okay, I'm wondering if I gave myself enough room here. So you start off with your priors and your two possible states. So we could sell 10K or we could sell 100K. Okay, and the prior probabilities of each of these are 0.6 and 0.4. Okay. From each of these, I'll maybe bring these over. Then we could do our market research, right? And we could compute our conditional probability, or we're given conditional probabilities. And so, I'm going to make these curved. I don't usually do them curved. And so let's put our conditionals in here. And so let's see, the sell 100K. And so let's look at UMC given that we sell 10K. And this one will be FMC given that we sell 10K. So both of these on this branch come from the sell 10K. And so these are going to be probabilities given that we sell 10K. And then we can do UMC given 100K and FMC given 100K on this branch. Okay. And each of these given or conditional probabilities are those accuracies that we were given at the beginning. So this is 0.85. This one was 0.15. And then we got 0.35 and 0.65. Okay. So these are the accuracies that were in kind of given, kind of our accuracies for our market research. Here are our priors. Okay, all of this is sort of information that's given to us. And now what we need to do is compute the joint probabilities. To compute joint probabilities, we multiply along here. And so we'll do UMC and 10K, and we'll multiply this times this, and UMC and 10K gives us 0.51. And then we multiply along here for FMC and 10K, and 0.6 times 0.15, that gives us the 0.09. And similar, we're going to multiply down each of these. They'll turn conditional ones into joint probabilities with an and. So UMC and 100K and FMC and 100K. And multiplying each of these down along there, this will give us 0.14 and 0.26. Okay. Then you got to essentially find your matching joints that have the same finding. And then off to the side, you'd need to do P of UMC equals, you find the two that have UMC, and that'd be the 0.51 plus the 0.14, and that gives you 0.65. And then P of FMC, you'll find the two joints that have FMC, so that'd be 0.09 plus 0.26, and that's going to give you 0.35. And then the last thing you do along these probability trees, we'll talk about decision trees in a little bit, is that then you flip the order and do it given. So this one will be 10K given UMC. And to compute this, you take the joint and you divide it by the corresponding unconditional or probability of finding. And so that's going to be the 0.51 divided by 0.65. And that gives you a probability of 0.785. Okay, and this one would be 10K given FMC. This would be 100K given UMC. And this one would be 100K given FMC. Okay, and then you do the same computations, you'll get the same posterior probabilities that we did before of, let's see, this, let's see, 10K and FMC, this is going to give you 0.257. This is going to give us 0.215, and this is going to give us 0.743. Okay, by taking, for this example, this one, we take the 0.09, we divide it then by the unconditional probability of FMC, so 0.09 times divided by 0.35 is going to give us the 0.257. Okay, so this is maybe a compact way to do those computations instead of having like just a whole bunch of sort of kind of a page of those computations and trying to remember what is. This kind of can organize things. So it's like you multiply along these to get this, you find the two ones that have the same finding, add them together to get the unconditional, and then divide by the appropriate unconditional to get the posterior. Okay. So once we have those posterior probabilities, now we're actually ready to use Bayes' rule. Okay. So Bayes' rule says we want to compute the expected value, and we'll compute the expected value under each possible experimental finding. Okay. So let's look at our alternatives and let's look at our experimental findings. So we'll put our findings up top. And so findings would be unfavorable market conditions or favorable market conditions. And then our alternatives would be either build or sell. So if we decide to build and the market conditions are unfavorable, the key here when we're computing these expected values is we're going to use posterior probabilities. And so we're going to evaluate the build alternative under both unfavorable and favorable market conditions, right? So under unfavorable market conditions, we're going to use these two probabilities. Okay, and so we'll have a probability of 0.785, which is the probability of 10K computers under unfavorable market conditions, times the value of selling 10K, which is 0, plus our other probability under unfavorable market conditions is 0.215 times the value of 54. And then we go ahead and multiply those out and add them up. And let me pause the video to pull up my calculator. Okay, I got my calculator. So we do this multiplication and the addition, and we should get an expected value of 11.6. Notice that the expected value for building has gone down in an unfavorable market condition compared to what we had when we computed our priors. I think it was 21.6. Under favorable market conditions, we'll use the posterior probabilities for favorable market conditions. And so that would be 0.257 is the probability of 10K under favorable market conditions, times the value of 0 if we sell 10K plus probability of 100K under favorable market conditions is 0.743, and that will be multiplied by the 54 million in payoff that we expect if we sell 100K. And if we do that multiplication, we should end up with 40.1. Okay, and so maybe I'll kind of put an extra column over here just for reference, is that we had a expected value of 21.6 under our prior probabilities. And so when we come back with an unfavorable market condition, the expected value has gone down for the build alternative, and under favorable market conditions, the expected value has gone up for the favorable market conditions. Now for sell, we get 15 million either way, and so I won't do the computations, but you do the same probabilities, 0.785 times 15 million, then 0.215 times 15 million, but we know that the expected value is going to be 15 million in both cases, as it was under the prior. Okay. And then I'll make one more spot down here for best. So under unfavorable market conditions, the best that we can do, we now compare the 11.6 to the 15, and we notice that, hey, if they come back and tell us unfavorable market conditions, we're better off selling our rights because that will give us a better expected value. On the other hand, if there's favorable market conditions, we expect to get 40.1 if we build, but only 15 if we sell. And so it's better to build. And so we expect a higher expected value from building than from selling. Okay. And so notice that under different findings from our experimentation, we have different alternatives that are chosen. And so in this case, that's the best alternative in that column versus that's the best alternative in this column. And then prior, kind of before, it was the 21.6. Okay, and so this is just for reference, but the best before was 21.6. And so now we've traded 21.6 for a chance of either 15, but 15 is better than 11.6 if we get the information of unfavorable market conditions, or 40.1. Okay, the last computation to do here is to compute an expected value with experimentation. Here we take the expected value of our payoff given a finding, and so those are actually these two values. Sort of the best, we're always going to choose the alternative with the best payoff, and then multiply by the probability of the finding. And so the probability of finding are going to be these unconditional probabilities that we had before. So computing that expected value with, I'll abbreviate EXP for experimentation, is going to be the probability of an unfavorable market condition times the expected value under an unfavorable market condition, plus the probability of a favorable market condition times the expected value of a favorable market condition. And these two are for the best alternative, is what I'll say there. And so this is going to be the probability of an unfavorable market condition. We computed up here to be 0.65 for that finding. The expected value of an unfavorable market condition, the best we can do under unfavorable market condition is sell, and that will give us 15 million. Plus the probability of a favorable market condition is going to be the other 35% times the expected value under the favorable market condition. The best we can do under a favorable market condition is 40.1. And if we do that computation, we should get, as a result, just around 23.8. 22.8. Okay, so we should compare that back to our expected value without experimentation was about 21.6. With experimentation, we were able to boost our expected value up to 23.8. So the value of the experiment is going to be the difference between the two. And so in this case, it would be 23.8 minus 21.6, or about 2.2 million. Okay, so is the 1 million that we pay for the research worth it? Yes, on average, doing the experiment will make us better off by, on average, 2.2 million. And so we'd be willing to pay that 1 million for the market research because the value of the information is 2 million. Or 2.2 million. Notice that this 2.2 million is quite a bit less than the expected value of perfect information. I think we computed, yeah, here's the right piece of paper. The expected value of perfect information is 9 million. And so of a potential 9 million that we could get from market research, we'd only expect to get 2.2 million. And that's because our market research is not perfect information. And actually, we used pretty low conditional probabilities for our accuracies. And if we had better accuracies, we might get closer to that 9 million. But we only had sort of 85% true negative rate and only a 65% true positive rate. So this true positive rate especially is what probably held us back from realizing more of that potential value from the experimentation. Okay, that's it for this already pretty long video. I'll do one more video to kind of wrap things up and show you how to build what's called a decision tree and sort of summarize everything that we found.